Good, yeah, good question to talk about. And the warm-up is a good one, too, to kind of tie up some loose ends of things we didn't really highlight yesterday. Just remember that you can't forget anything ever, right? View substitution? No, sorry, you gotta do it right now. Here, go for it. Let's talk about two other kind of situations that we could run into that can be the integration by parts can handle. Though we need maybe a little bit of, we need to have a little discussion maybe about how to handle these. Where did my, sorry, this is like the old slide. Did I still have this on here? Where'd my, oh, there we go. Okay. That was the slide from yesterday. All right, let's see if we can handle this guy right here. Looks not too bad. Looks like a good integration by parts one. Let's let so we have e to the x cosine x. What would you like to let u be? L-I-T, no. E, T, and actually I told you those are interchangeable. We'll go with e to the x, okay. But someone else, just for fun, if you're kind of see where this is going, feel free to let u be cosine x. You'll also have a great time with this as well, okay? So I think it's just, we said e, t, because it sounds good, lip it, but it could be t, okay. Lipte, it could be fine. Anyway, so yeah, let's let u be e to the x, and just see how this goes. We'll run. The first half of this is going to feel great. You're going to love this. Okay, so here we go. First half of this, yes, right. Everything's going great. Everything's feeling good. Cosine x dx. I love taking the derivative of e to the x. I love anti-differentiating cosine x. It's my favorite thing. Sorry, what am I writing? Yeah, so here. uv minus the integral of v du. I think I had that memorized now, don't I? uv, kind of rolls off the tongue, doesn't it? Minus the integral of v du. So far, so good. Feeling good. And this feels like yesterday too. You're still not daunted because you're thinking, well, we can do integration by parts again, right? No big deal. So let's let u be I guess e to the x again. Du equals e to the x. I feel like I've done this before. dv this time will be sine x dx. V is equal to negative cosine x. You tell me when we're having fun, okay? All right, so we have this integral. We'll substitute now with uv minus the integral of v du. Okay, let's hit pause for a second and make sure you're following all that. It's just integration by parts twice, right? So far. Now, and let me clean. Maybe we clean this up a little bit too, just for those who might like to see it a little cleaner. What is that? E to the x cosine x. Got a minus and then two more minuses. How about a minus e to the x cosine x dx? Just verify that the algebra is good so far. Everything looks good. Now the only issue is, how does this feel right now? Like, it feels like we're not really getting anywhere. It feels like spinning our wheels, doesn't it, a little bit? In fact, you already felt that way up here. You're probably like, I will do integration by parts for you, Mr. Chase. But I already kind of feel like that's not any more or less difficult than the original problem was. Like, have we made any progress? I didn't know that derivative. I didn't know the antiderivative e to the x cosine x. How is this better? Anyway, so this doesn't seem like we're making progress. So we can do integration by parts again, if we like. But I think you can see that would be. We could just do it an infinite number of times. That'd be cool. over and over again. All right, well, let's just kind of stop and see where we are in life just for a second here. What does this equal? What does this equal? Oh yeah, the thing we started with, I want to make sure we're focused on the beginning of this chain of equalities. And I want you to stare at this for a second, okay? Because the thing you want in life, let's call it W for the thing you want in life, okay? Okay? We call it W for the thing you want. This is equal to, so you see this thing here? This is the thing you'd like to know. Do you see the thing you want to know anywhere else? I do. Do you see the thing we want to know? Called W. Somewhere else? I do. It's right here, yeah. So, I don't know where I'm going with this. But I do know that the thing I want to know, we'll call it capital W, is this is certainly true, that e to the x sine x plus e to the x cosine x minus the thing I want to know is equal to the thing I want to know. How might you find the thing you want to know? Think it might be time to outsource this to our friends in Algebra 1, right? Any chance we can solve for W? Anybody? Let's give it a try. Here we go. I don't know what I want to know, but I do know 2 times the thing I want to know is that. So the thing I want to know must be, yeah, half of this stuff. Plus C. All right, now we're being cute with the W, but we could go back and put the actual integral in there. Right. You don't have to. The W is fine too. I just mean maybe we can handle seeing it over and over again. By the way, feel free to differentiate as usual to check, right? 1/2, our final answer, 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c. This technique is called, appropriately, solving for the unknown integral. Okay? Come up with really, really creative names for stuff. It's as accurate names as we possibly can. So that will happen a lot of times when you have 2 functions that just basically never go away, right? Any other thoughts about that? I don't have anything. I mean, once you've seen one of these solve for those unknown integral problems, I feel like you've got the idea. You'll be fine trying some more of those tonight. But that's what it feels like. There's this moment of despair and then this moment of epiphany, isn't it? You're like, this is never going to end. And then you're like, oh, wait. Right? Isn't that how it feels? You're like, oh, wait. Maybe the fact that I keep getting the same thing is a good thing. So when you step back from this, you're like, was that worth it? I mean, that's a lot of work for one integral, but I think it was worth it. I mean, that's a good integral. Okay. We did this problem yesterday in your notes. And do you remember how it felt? If you look back just a page in your notes, what did we do with this one? What was required of us? Yeah, you could just read the slide, I guess, too. That's right, yeah. No, I forgot. I wrote it up there, I guess. Do you remember this, though? We used integration by parts twice. Even if you don't remember the details, you don't have it right next to you in your notes. You can even see maybe that this is going to take integration by parts twice, just by the form of it. You're going to let u be x squared. It's not going to quite go away. You're going to have to do it again. That's how it felt, kind of. All right, well, capitalizing on that observation that this feels like there's some systematic stuff happening that we could just kind of maybe turn into some kind of a procedure, an algorithm. What we're about to teach you is really truly just an algorithm, okay? It's nothing more than just a way of organizing multiple applications of integration by parts, just to organize our work. So I hesitate to even call it like a new method, per se. If someone asks you to do integration by parts, the thing we're about to do is integration by parts, okay? So here's a little slick way to organize our work. And when we're done, just compare and see that, please, and we get the same answer that we did yesterday, okay? Because you have it in your notes somewhere, right? Okay. So the first thing we're going to do is we're going to choose a u value just in the same way we've been doing. So let u be x squared, right? And then that makes dv e to the x dx. So we'll call this function g of x in the right column. And here we'll take derivatives, and that should make sense based on what we did with integration by parts. But we'll take repeated derivatives of this because we know that that's kind of how that felt yesterday. And in the right, we'll take repeated integrals. At the end, we'll add a c, don't worry. Thank you for keeping us honest, though. Appreciate that.
What happened?
We will. Nothing happened, actually. Really nothing at all. Now I'm going to come along, again, for reasons that come right from the integration by parts formula. Do you remember this feeling? You're like minus, and then in parentheses, another integration by parts formula. So what's the sign on the next integration by parts formula? Well, really it's plus, isn't it? Or then really, if you do integration by parts like 5 times, you'd have like all these nested sets of parentheses, and the sign would alternate in between each one. Because you have like a minus out front, it would like cancel out, and then you'd have like a minus. So that's the reason I'm about to do the following. Put a plus out front in front of the first column, and then a minus in front of the next column. You following? And then a plus. And if there are more rows to this table, keep doing this. Add a plus in front.
I know.
Oh, why? So the first term of your integration by parts. Well, here, let me throw those out front. The first term of your integration by parts formula, when you do the integration, is x squared e to the x. Do you remember that? It's u v, right?
Yeah.
And then it's minus the integral v du. But then why is it going to be a plus? Well, because if you have like those nested parentheses, you're always going to get the opposite sign every time as you go from one integration by parts formula to the next. So that's the reasoning around why this procedure kind of works. We didn't flesh out all the details, but I've given you an idea of why it's working. Then we multiply these, a little tic-tac-toe, right? Add them up, and there's your there's your answer. Is that what we got yesterday? Check, check, check. Or just take the derivative again. There's the plus c. So please don't be like, oh my word, you've just given me fire. Or the ability to like do these integrals quickly and powerfully. Well, just don't forget where you came from. I mean, this really is still just integration by parts. It's just like us noticing that there's this pattern and like capitalizing on it, right? That's all. There's nothing. There's nothing more than that being done. Did anyone bet the answer, by the way? Is it actually right? Just check it, please. Okay, that's the same answer we got yesterday, or you can take the derivative and check and make sure it's right, too. So, what did we just do again? All right, here are the things you just did, in case you didn't know. Okay, you used lipit to choose f of x in the same way you might choose u for that first column, right? And then g of x is like the v minus the dv part, right? And then you made a 2-column table, took derivatives of f until you get to 0. Just keep taking derivatives. So that's why f really needs, in order for this to be like a finite process with an end, so that we don't get like an infinite series here, then we would like to eventually, a good choice of f is one that differentiates to 0 in finite number of steps, okay? Yeah.
Are you finding you chose lipid because in that order it integrates to that number?
Yeah, it's about how fast they disappear. Yeah, how fast the integrals disappear. Except, yeah. the inverse trig maybe is a little trickier to say about, but yeah. And then G, we're taking integrals. I just want to say what we just did. That's all. And there's nothing new on this slide. I just want to say what we just did in case you forgot. Okay. So make 2 columns. This is like make your choice of F the same way you make your choice of U from yesterday. Take derivatives, and in the right column is the leftover function, G, we'll call that. Take integrals, make sure that's an integrable function. That's like, that you know the symbolic integral of. And then alternatively label your columns plus, minus, plus, starting with plus, going all the way down. And then without using the first entry in the second column, multiply diagonally. I don't know how else to say it in words, you gotta see the picture. Okay, like that, and then write down your answer, don't forget the plus. Nicholas.
Can we do this kind of shortcut?
Absolutely, yes.
Is that how they show up?
Yeah. Now, is it worth doing tabular for like if only integration by parts is necessary 1 time or even 2 times? It's not like actually a huge time saving. Where this really shines is when we like integration by parts would be required like 4 times or 5 times. Then you're like, then it gets a little. It's nice to have something like this to organize your work and give you a little bit of a shortcut. Let me. I'll throw this back up here in a second, but let me. X cubed sine x is the next one. X cubed sine x, if you want to start working on that, we can too. X cubed sine x is the one we're going to do next, okay, on the next slide. So if you would like to get started on it, you can. Using this technique. Yeah, please. Make one.
So there's a third part, like if h of x, you get to add another column to your table.
No. G will just be the leftover part, which hopefully has an integral. Yeah. No, there are only ever 2 columns for this. And again, it comes all any question you have, we can take back to the method we talked about yesterday. This is all just still integration by parts. So it's really not actually any more powerful than just normal integration by parts.
Depends on the mood I'm in.
Do you want to live on the edge?
Sometimes,
Whatever you have.
sometimes even the highlighters, you know?
That's
Sometimes I just run
I'd love to work this problem in a second here, but is that those who would like to write down the steps, have you at least captured them in shorthand at least? Take a picture or something.
You know, there's a line environment, right? Hey, Alfred.
Yeah.
Alfred.
All right, so are we good? Can we do this together? Those who've already started are probably already done, right? I mean, it's so quick, really. It's fun. Okay. So F and g, and it's derivatives and integrals, so we get x cubed here. And sorry, what should u be? X cubed. Okay, sorry, I should have asked. Okay. And then take some derivatives. Love the power rule, just love it. By the way, check your answer if you like at the end too. It's not too bad, right? All right, now integrals. Integrals over here. So we get negative cosine, negative sine, cosine, sine. Nice little pattern going on there, right? Plus, minus. Okay, here we go. Now we can just like write down the solution, can't we? It's so great. Negative x cubed cosine x. Tick, tack. I gotta make sure I actually hit these right. Boom, boom. Plus 3x squared sine x minus, no, plus 6x cosine x minus 6 sine x plus c. It's actually not, even though that looks terrible, it's actually not that bad to check this real quick, is it? Right? Every time you'll have like the garbage collection field, right? Won't you? Like we talked about yesterday, right? Let's do it. Let's do it real quick. Take the derivative of this, you'll get x cubed sine x, yes? And you're like, yes. Except, what else spits out? Oh yeah, that's right, a negative 3 x squared cosine x, right? Which is perfect because this, when we take a derivative of this, we get 3x squared cosine x and cancels out with that. But we also get 6x sine x, which is okay because when we take the derivative of this, we get 6x sine x. That cancels out. Plus also 6 cosine x, but that's okay because the derivative of this is negative 6 cosine x. We're good. So you can see that it's actually not too bad to check these, even terrible ones that look terrible like this. Can we do this one before we leave? This is my last slide. See if you can do it before the.
Awesome. Okay.
See if we can do it before we go. Okay. Careful with your integration on these. I'll do this column for you. That's nice of me, right? We got a nice long answer on this one. It's going to be great. What's the antiderivative of e to the negative 2x? Now I'm asking you to do this in your head here. Can you do it though? Sure you can. Antiderivative here. Negative what? Negative a half e to the negative 2x. Take the derivative and see that that's the right antiderivative. Okay. All right, now I think you're on the right track now, right? Keep anti-differentiating this. It's a lot of integration. That's integration by parts 4 times we're about to do, right? What is that? Negative a half x to the 4th e to the negative 2x minus x cubed e to the negative 2x. You want to simplify fractions? 12/8. Just write it as 12/8. Feel free to simplify these fractions. Have a great day, guys. All right, have fun with homework 2 tonight. You're going to love it.